All right. Hello, everyone. My name is Marcos Semenovich, and today I'll be presenting our work, TinyLSTM's Efficient Neural Speech Enhancement for Hearing Aids. And before I go on, I should mention that this work is a collaboration between our group at Bose, where we work on machine learning-based signal processing, especially with an eye towards hearing assistance, and the ARM ML Research Lab in Boston, where those folks work on shrinking down all sorts of deep learning models for resource-constrained and embedded devices. So as the name implies, our work focuses on compressing deep learning powered speech enhancement to a size, power budget, and quality that could be deployed on a hearing aid. So modern speech enhancement networks, as many of you know, yield game-changing noise suppression compared to techniques that are in industry today. The issue is that deep learning is compute intensive and memory hungry, and hearing aids by design need to be tiny devices that you can fit in your ear or behind your ear and that need to last all day. So these two needs are at odds with each other. And when we look to the literature to address these issues, we find a rich body of work in speech enhancement and an equally rich body of work in model compression, but very little on the intersection of those two fields. So in this particular work, we aim to bridge that gap. First, we start by setting some computational constraints by choosing a piece of silicon that could reasonably power a hearing device. We end up with the chip and compute constraints you see listed on the bottom left of this slide. The next thing we do is we train a baseline speech enhancement model to a reasonable quality, and then we go on to try different techniques to compress this model down to a size and quality that would be reasonable to fit on this chip and that would still be usable. Finally, we verify the quality of the networks by doing perceptual studies, since the output of this model is meant for human consumption and isn't just the output of a classification network. All right, so our baseline model. We start with a baseline model that is a two-layer LSTM with two dense layers. The input is a power law MEL spectrogram, and the output is a time frequency mask that gets applied to the original spectrogram to come up with the denoised output. By any account, this is a tried and true speech enhancement architecture. And here I'll argue that RNNs are inherently well suited to the low resource, low latency frame-by-frame audio processing that we care about so much for this task. So although other network structures like TCNs, UNets, WaveNets, and other CNNs have shown a ton of promise for a variety of signal processing tasks, like speech synthesis, source separation, speech enhancement, they do have drawbacks for low latency inference. So the first thing I'll mention is that CNNs use much larger intermediate representations than dense layers or LSTMs, and this just uses memory that we don't have on a low resource device. Secondly, they tend to have higher MOPS per model due to parameter reuse. So although CNNs generally can be quite efficient in the number of parameters in the models themselves, those parameters get reused a lot and they're used quite inefficiently, which leads to a higher compute usage. And the last thing that I'll mention is that CNNs, they necessitate large receptive fields to explicitly capture the temporal dynamics of the audio that preceded the current sample. In contrast to this, RNNs process audio frame by frame, and they model temporal dynamics by building up that audio into a compact state vector. And this is just a much more efficient way to model those dynamics. So moving on to the main course. We apply three distinct compression techniques to our models. First, we do structured pruning to try to decrease the size of the computational graph. Second, we apply training-aware quantization to decrease the size of the data types and model the fixed-point arithmetic that we'll need to deploy on an edge device. And finally, we use skip RNN cells to try to induce conditional execution and let the network not infer when it doesn't need to infer. All right, so getting into structured pruning. At a high level, what pruning does is it aims to reduce the model parameters with minimal performance drop-off by removing weights from the model that aren't contributing much to the model performance. So in plain English, as the model weights get smaller, you try to kind of reduce those weights that are smaller. And there are two kind of high-level approaches to pruning. The first is random pruning, and that's where you pluck out specific weights out of a weight matrix. And the second is structured pruning. And in structured pruning, you also prune the matrix, but you pluck out blocks of weights instead of just single weights at a time. And we choose structured pruning since it provides the added benefit of not requiring any additional hardware acceleration or hardware instructions, such as support for sparse tensors, to be deployed in an edge device or microcontroller. And I'll mention that The type of structures that we decide to prune, the type of blocks that we decide to prune, are entire rows of the weight matrix. You can think of the pruning as being analogous to plucking out actual neurons out of layers of the neural network as we train it, so the network gets smaller and smaller as we train. And we choose which rows to prune based on their L2 norm. And we add an additional term to the loss function that you see down at the bottom here to induce the model to sparsify the network. So we determine when to prune this row based on a threshold. We initialize this threshold to 0, and then along with the weights, we learn that threshold, and that threshold starts increasing. So as the model starts, the threshold is 0, and there's no pruning involved. And once the quality of the model gets to a certain level, we begin pruning, and it becomes kind of a balancing act for the loss function to balance the level of sparsity with the level of quality. The one hyperparameter that we introduce to control the level of sparsity is this lambda that's a degree of pruning. So how do we determine the threshold? Well, we actually learn it right along with the weights. And the way that we do this, since thresholding is a discontinuous function, so you can't backpropagate through it, we introduce an approximation of the thresholding function in the backwards pass. And one thing to be careful of when pruning LSTMs is the interactions between the gates and the tanh and the states in the intermediate representations inside the LSTM cell. So when you're pruning those, you have to make sure that the shapes of all the outputs of those are the same, otherwise you won't be able to apply the gates. It just won't fit. So in order to mitigate this, we group all the weights that may have interactions. So it's a higher level grouping than just our rows in the LSTM cell itself in order to prune the LSTM cell. However, we can apply this type of pruning to dense layers as well, and actually any layer in a neural network. We just have to be careful about the structure. And in our implementation, we apply it across the entire network as we train. Okay, so next we have training-aware quantization. The idea here is to use 32-bit floats to train, but to approximate the resolution and dynamic range of fixed-point data types in order to make the model resilient to quantization errors. Often when quantization is applied to neural networks, folks will just quantize the weight matrix or maybe quantize the bias. This happens in literature quite a bit. And this is useful for saving memory space for the weight matrix. So you can save the weight matrix as 8-bit and then load it back as 32-bit. But it doesn't really model all of the fixed point integer arithmetic that we're going to see in an embedded device. So in order to accurately model that, you really have to model quantization on all the points that we have on this figure. So you need to quantize input, the weights, the bias, and the activation. And all of these different quantization nodes will have different dynamic ranges that we learn end to end. One other thing that I'll mention here is that we quantize everything to 8 bits, but we leave the time frequency mask, which we apply to the spectrogram, at 16 bits. And we do this to allow enough resolution to accurately apply the gain vector to the audio. All right, so our final compression algorithm is skip RNN cells. As I mentioned, this is adding conditional execution to the network. Another way to think of the skip RNN cells is as dynamic pruning in time. So the intuition here is that we don't need to update the mask values when the signal is stationary or when there's very little signal, and try to not call the network when we don't need it. We introduce an additional cell ahead of the expensive part of our network, which is the LSTM cells, and we try to get this skip RNN cell to learn when it can turn off the expensive part of the network. So it's kind of building up a probability that it can turn off, and when it kind of hits a threshold, it'll turn off the network or the LSTM cells for a few time steps, and then it'll come back online. So although this doesn't affect our evaluation metrics that much, we noticed that perceptually this induces some annoying audio artifacts into the signal. And to kind of mitigate those artifacts, we apply an exponential smoothing average across the time frequency masks with the skip RNN cells. So while this helps mitigate some of those artifacts, it does induce a little bit of bleed through of noise. All right, so here are our results. So what you're seeing, so the top line is the baseline, the second one is our prune and quantized model, and the third line is prune and quantized with the addition of skip RNN. You see that both of our models lose about half a dB of SISNR compared to baseline, which is a decent amount, but not a lot. But when you look at kind of the savings on the model size, we save an order of magnitude of compute compared to the baseline. And we save a factor of 3 in computational latency and MOPS per inference. And so we think this is actually a pretty good trade-off. I'll play some audio for you so you can get a feeling of the difference between compressed and uncompressed. So here's the noisy speech.
The May slump, reported June 22nd, came as a big surprise to most analysts and helped trigger a powerful bond rally that day.
All right, here's the uncompressed.
The May slump, reported June 22nd, came as a big surprise to most analysts and helped trigger a powerful bond rally that day.
So that's our baseline model.
The May slump, reported June 22nd, came as a big surprise to most analysts and helped trigger a powerful bond rally that day.
All right, so this is our pruned and quantized model. So this is an order of magnitude smaller than our baseline. And finally, with skip RNN.
The May slump, reported June 22nd, came as a big surprise to most analysts and helped trigger a powerful bond rally that day.
And with the skip RNN, you can kind of hear some of the audio artifacts bleeding through, and that's kind of due to the exponential moving average that we've added there. But with the skip RNN, you can also see that we save an additional 50% on compute. One thing I'll mention is that the items in red note that they violate our compute budget, and you can see that they violate it by quite a bit. So model size here is 3.7, and we need less than 0.5 megabytes. Okay, so on to our perceptual study. What you're looking at here, the y-axis is preference of the model output versus noisy speech, and x-axis are the different SNRs. The gray line is the uncompressed baseline model. The orange line is the pruned and quantized model. And what you're seeing is that the gray line and the orange line are basically sitting right on top of each other. So we did a statistical significance analysis, and it showed that there's no difference between preference for compressed and uncompressed. Both provide an equal benefit, even though we take a bit of a hit on the metrics. All right, and finally, we're comparing our perceptual study for our speech enhancement models on the left to a similar study that was done for a product that we have in the market. This is preference for directional processing from Bose earphones. So this is basically using beamformers to key in on speech. And what you're seeing when you compare is that the compressed model provides higher preference ratings than the directional processing that we have in production today. So there's a lot to gain by getting this technology out to customers. And finally, some takeaways. So the main thing that you should take away from this talk is that it is possible to run high quality neural speech enhancement on today's hearables and microcontrollers. So this is really exciting. This is here today. We don't have to wait for some next generation of embedded neural accelerator. These things can be deployed today using the techniques we talked about. And that's pretty exciting because it enables a lot of new possibilities and new products, and it'll enable us to get this kind of technology into people's hands. Also, we take our results and compare them to the state-of-the-art LSTM models. We show an almost 12x reduction in model size. We show about a 3x reduction in the amount of compute that's necessary, and the trade-off is only 1.1 dB of SNR. And on top of that, we do perceptual studies and show that people don't even notice that for the most part. There's no detectable difference between a full quality model and a compressed model. And so that's our talk. Thanks for listening, and hope to see you guys in the virtual poster session. All right, take care.